Welcome to today's webinar. My name is Andy Purvis. I am the General Manager for Europe, the Middle East and Africa with the Global CCS Institute. I'd like to welcome participants from around the globe to today's webinar, and it will be my role to introduce this webinar to you. This webinar is one of a series of CCS-related webinars on key topics which the Global CCS Institute are delighted to bring you. I would like just to start with a couple of housekeeping rules. We've scheduled 1 hour for today's webinar, and we will certainly keep to that schedule. We will also make slides of the webinar and a recording of the webinar available within a few days via the Institute's website. I would like to start by introducing the topic of our webinar today, which is CCS as least cost option for integrating intermittent renewables into low carbon power systems. We have a couple of high caliber speakers to present this subject today. So I'd like to take a moment to introduce our panelists. Our first panelist is Dr. Machteld van den Broek. Machteld is an assistant professor at the Copernicus Institute based at Utrecht University. She has a long history and certainly a lot of credibility in the low carbon energy space, having worked in power system modeling, design around heat supply, energy efficiency, and CO2 capture, transport, and storage. She's also been a work package leader in a number of European Union funded projects and coordinates an energy modeling course at the Utrecht University, where she also supervises PhDs and master students. So, Machteld, you're welcome today. Our second presenter is Anne Sjoerd Brouwer. Anne Sjoerd is a PhD researcher at both the Copernicus Institute at Utrecht University, but also the Policy Studies Unit of the Energy Research Centre of the Netherlands. Anne Sjoerd has some history in CCS, having been involved in the Cato-2, well-known Dutch national research program on CCS. He's also been well published in peer-reviewed publications and journals in the US, Japan, and the Netherlands. I will now give you something of an overview of how the webinar will work practically. During the presentation, you'll see a panel on the right-hand side of your screen. At any point during the presentation, you can type your questions here as we go through the presentation, or during the question and answer section, which we'll get to at the end. I would really encourage you to ask questions as we go through, as this can really add value to the webinar and the presentation. We will compile the questions as we go, and I will ask as many as I can of our panel during the time we have allocated. Obviously, if we have similar questions or questions that can be sensibly grouped together, I may look at doing that in the interest of time. I would now pass over to the first of our presenters, Machteld van den Broek.
Okay, thank you very much, Andy. Welcome everybody to our presentation of this study, where we investigate how CCS can contribute to a power system with a lot of intermittent renewables. We are doing that from the Copernicus Institute, and the Copernicus Institute, we want to look at innovative processes, try to identify them to get the world to a sustainable world. For this purpose, we have 4 research groups in our department. That is the Energy and Resources Group, Environmental Governance Group, Environmental Science Group, and Innovation Studies. We are part of the Energy and Resources Group. In the Copernicus Institute, we have 5 main themes. That you can see that on the slides. That is bioenergy, smart cities, and energy efficiency. Also resources. In this resources topic, we also do CCS topics like utilizing CO2 in very innovative processes and what will be the impact. In geo-resources, CCS is also a big research area. And we have, well, overlapping themes, and one of them is the power sector. The power sector is a very important area, of course, because it is now in a state of transition. We want to get to very low carbon electricity systems, and at the same time, a lot of intermittent renewables are entering the electricity system. And we need to know, well, how can you develop this in the best way? And there are emerging technologies like carbon capture and storage, electricity storage, and increasing interconnection capacity. At the Copernicus Institute, we are looking with detailed modeling at how the electricity system can develop. We are doing a number of activities in this. Well, these research projects we are doing in the power sector here are a few examples. At the moment, we are looking at the combination of biomass in relation to CCS and how they can combine in the power system and also the whole energy system like the transport sector in the Netherlands. And results will be out at the end of this year. We are also looking at the CCS in the industry in a detailed way. In 2 weeks, the PhD thesis of Niels Berghout will be out and online. In this thesis, we also looked at the power sector. 1 year ago, I presented one study, and that was on the role of natural gas combined cycle power plants with CCS in the electricity system. In the meantime, the article is online, and I have the website here. You can see it. If you cannot find it or you have additional questions on this article, please email me. During this study, we found that we didn't know enough about the power system to really assess what could be the role of NGC CCS. So that is why I initiated the study we are presenting during this webinar. And in this study, besides Anne Sjoerd Brouwer and myself, also Will Zappa and Wim Turkenburg and André Fay were involved. So I want to hand over the floor to Anne Sjoerd Brouwer, who will present the whole study. Thank you very much.
Thank you, Machteld. Good day, everybody. I'm Anne Sjoerd Brouwer, and I will present the main findings of our work. I will start by giving a bit of background on intermittent renewables, which we will also call IRES in this presentation. I'll follow up with some words on the method, the results, and finally the conclusions. But first of all, some background on intermittent renewables. When you look at low carbon power systems, you see that intermittent renewables may become a very important component of these systems. If you look at projections for Europe, for example, you see that by 2050 they may generate between 20 to 80% of all electricity, which is a lot. What is interesting about intermittent renewables is that they have very specific properties that you don't really observe in other types of generators. First of all, they're intermittent, so they generate when they generate, when the wind blows or when the sun shines. Secondly, they're partly unpredictable. It's good to mention that intermittent renewables are mainly wind power and solar PV power. And predictions for these two sources are pretty accurate, but there's always a degree of uncertainty which has to be accounted for. Thirdly, they're location specific, which means that the site of generation might not be the same site as where electricity is required, so more transmission might be needed. These three specific properties affect the whole power system. They affect the operation because Intermittent renewables, when they generate, the rest of the power system has to accommodate for their generation, and when they do not generate, the rest of the power system has to step up. The residual load, as it's called, becomes more variable. The residual load is the load that the rest of the power system has to generate. Secondly, also the economics of the power system may change because of two reasons. First of all, electricity prices may decrease because of intermittent renewables, because intermittent renewables have very low marginal costs, which lower electricity prices. And secondly, also the running hours of other power plants might decrease. Their capacity factors decrease because they have to account for intermittent renewables, and this affects their business case. Having said that, some technologies match better with intermittent renewables than others. And the question is, which technology should you invest in the future to have a system which can accommodate them well? And more specifically, the question is, what is the role of carbon capture and storage in this? Is it a good match, or should we look for other options? The goal of our research is to identify which technologies may be part of a power system with a high reliability, low emissions. We're talking about 96% emission reduction of CO2 emissions compared to 1990, which is a very stringent reduction target, and also the lowest cost. What we've done, we've simulated power systems with high shares of both RES, so renewable energy sources, and intermittent renewable energy sources to see how these future power systems can be realized. I would like you to consider a future power system in Europe in year 2050. This is what we focused on in this study. And what we did is that we simulated a 6-node power system with PLEXOS, which is a commercial optimization simulation tool for the power sector. As you can see in the picture, we looked at Western Europe with 6 main areas which all have their characteristics, and they have specific sources of intermittent renewables and different climate patterns. We evaluated 3 scenarios with 40, 60, and 80% renewables, and this corresponds to 22, 41, and 59% intermittent renewables as a percentage of the total annual electricity demand. As Machteld also said, there are a number of options which can play an important role in future power systems. You can think of electricity storage, interconnection capacity, new types of power plants, demand response. But the problem is that if you want to compare these options, that they're so fundamentally different in nature that it's really hard to make a direct comparison. That's why in this study we took a different approach and we looked at the system costs. So we simulated the systems with varying shares of different technologies, and then we observed what the effect of that is on the system cost. And in this way, we were able to compare these technologies in a comprehensive and objective way. Our methodology consists of 4 steps, which I'll quickly explain to you. In the first step, we define a non-fossil generation capacity for each of the 3 scenarios. As you can see in the picture here, we have different types of generators, but all I would like you to get from this picture is that we have the 40, 60, and 80% RES scenario, and then with that when you have more renewables, that mainly involves having more solar PV and more wind power. On the other hand, if you have more renewables, your fossil capacity and your nuclear decrease. So those are the 2 trends that you see. The other types of generation stay relatively constant. These capacities have been adopted from previous studies. Next, we define the capacity of complementary options in the second step, and we include 3 complementary options. We include electricity storage, interconnection capacity, and demand response. To give you a quick example, if we look at electricity storage, we added electricity storage capacity as a percentage of peak load, which you'll see later on. And what we accounted for are cost reductions due to learning. If you look at the picture here, you can see the present day costs in the year 2015 for 5 types of electricity storage and the projected cost for the year 2050. As you can see, there are significant cost reductions, especially for batteries. And overall, from our projections that the model can invest in, we consider gas turbines, natural gas combined cycle plants, NGCCs. They're called NGCC plants with CCS, coal-fired power plants with CCS, nuclear power plants, and dedicated biomass-fired power plants. So with steps 1 to 3, we now have a complete generation mix. And in step 4, we run hourly simulations for this complete mix. We run chronological simulations with almost 9,000 steps per year, hourly time step. And we account for flexibility, constraints, and reserves. In these simulations, we also allow for the curtailment of renewables. Having done that, we get the total system costs, which we will present now to you. And it's important to realize that you can reduce total system costs in 2 ways. First of all, you can have least cost power generation. And secondly, you can make the whole system more efficient with the complementary options, so storage, interconnection capacity, and demand response, which can make the whole system as a whole operate more efficiently. First of all, I would like to show you what the cheapest way would be to generate power in low carbon power systems. And I'd like to introduce you to this picture. And what it shows is the least cost, so the cheapest generation option with the lowest levelized cost of electricity for a CO2 price of 70 euros per ton. And this is dependent on the capacity factor, so the percentage of the hours in the year that the technology is generating. This is depicted on the x-axis. As you can see, at low capacity factors, demand response is a very cost-effective option because it has relatively low investment costs, and then it doesn't matter if the generation costs are a bit higher. It's followed up by natural gas combined cycle power plants, NGCC power plants, that is, which are next followed up by NGCC power plants with carbon capture and storage, which have more of a mid-merit to baseload capacity factor. And lastly, if you have very high capacity factors, coal-fired power plants with combined with carbon capture and storage can be the least cost power generator. In practice, though, the NGCC power plants generate too many CO2 emissions, so both the dark purple and the light purple area are in practice light purple. We see a lot of NGCC CCS being put in the power system, considering our assumptions, which you can find in complementary slides. However, what we see is that the demand response potential is limited. There's only so many gigawatts of capacity you can install. And the system needs more capacity than that. So when it's run out of demand response capacity, gas turbine capacity is put in place because it has very low investment costs. To make it a bit more complicated even, you can also consider electricity storage as a way to generate power by shifting power generated during hours of low load to hours with peak load. To show that in this picture, you can look at the y-axis, which shows the electricity storage charging cost, which is the electricity price when the electricity storage is charging. What you can see is that at low prices, so let's say up to 40 euros per megawatt hour, compressed air energy storage and pumped hydro storage could be theoretically a cheap option to generate electricity. At higher prices, at higher charging prices, regular power plants are still cheaper. In practice, though, there are two constraints which are depicted in the picture here. The first constraint is that you cannot really realize high capacity factors with your electricity storage because your electricity storage also has to store. So roughly speaking, you can get capacity factors up to 50%. You can consider that realistic. Secondly, we observe that electricity prices are too high for electricity storage to be the cheapest option in this study. The light blue line shows the electricity price duration curve for the whole year. And as you can see, there are very low prices for a limited number of hours in the year, let's say up to 3% of the hours you can have cheap electricity prices. But this is not high enough to make your electricity storage competitive because it needs higher capacity factors. It will need at least, let's say, 7% of the time cheap electricity prices. So overall, we can see that there's lots of natural gas capacity being installed. So gas turbines and NGCCs, that those are the cheapest options, and that storage can be attractive, but in practice it isn't. If we look at our simulation results, our optimization results, we see a similar, we see this in practice. If you look at the left figure, the installed capacity over here, you can see the total installed capacity for a number of generation technologies for the 40, 60, and 80% RES scenarios. To put it in perspective, we also put the existing capacity there and a 0% IRES capacity scenario. You can see that significant amounts of NGCC capacity with CCS are installed. That's the light purple, and it decreases as you have more intermittent renewables in your system. In addition, you can see that there's lots of gas turbine capacity installed. This is a lot, so you're talking about 200 gigawatts in the 80% RES scenario. This is capacity that's required to maintain system reliability. Because if you look at the generation in the right picture, you can see that if we focus on the gas turbines, that the gas turbines actually generate very little electricity themselves. This is partly the result of the high CO2 prices, and also partly because other options are actually generating the power. The gas turbines are just needed to maintain system adequacy, because the firm capacity, so the capacity that you can always rely on, that is delivered by solar and wind, is relatively low. Shifting back to the NGCC CCS capacity, you can see that this is a major source of electricity production, and it decreases slightly when you go to higher penetration of renewables, but this is the key complementary technology. To give you an idea of how these power plants operate, this figure provides the average monthly generation, so the capacity factor for every capacity factor during the day on the top and during the night on the bottom, for the 12 months of the year for a selection of technologies. As you can see, in Europe, solar PV production peaks in summertime. The wind production in blue is relatively constant throughout the year. And NGCC CCS power plants, they complement the solar PV generation here. They generate a lot of power when there's high power demand in wintertime, but there's hardly any solar PV generation. And in summertime, they provide less power. As you can see, the gas turbines during the daytime hardly generate anything. During nighttime, the picture is different, however. You can see that when the solar PV is not generating during nighttime because there's no sun, the NGCC CCS is generating pretty constantly at the mid-merit to base load position in the merit order. To illustrate this a bit more and to draw a comparison with electricity storage, I would like to show you a typical summer and a typical winter week of the year. And if we just focus on the NGCC CCS in this picture, which is the light purple again, you can see that it is generating a little bit of power during the day when solar PV peaks, and during the night it provides actually quite a lot of electricity. This is actually a type of generation that electricity storage could also provide when it charges during the day and then it discharges during the night. However, when you look at a winter week, you can see that in wintertime, as also shown in the other picture, that the NGCC CCS is generating pretty much constantly, also during the day. And this is actually a type of generation that will be very costly to replace by seasonal electricity storage. In addition, you can see that the gas turbines provide peak demand here when wind and solar PV production are both really low. Shifting to another topic, the CO2 emissions of the whole power system, we can see, interestingly enough, that the CO2 emission reduction target is met in all scenarios. If you look at the picture below, you can see the CO2 stored for each of the three scenarios, the 40, 60, and 80%. And the colored stacked bar shows the actual emissions resulting from three types of generators. The diamond shows the specific emissions in grams per kilowatt hours. You can see that there are some slight variations. This is due to the modeling approach, which makes it really hard to get exactly the same emissions. But overall, you can see that these stringent emission reductions can be achieved in all scenarios. The differences are that you store less CO2 in 80% rest scenario because you have less NGCC CCS capacity, and that other types of generators, so the gas turbine and the NGCC, have more budget or emission budget to also run more, so they generate more CO2 emissions compared to the other scenarios. Looking at the total effect on the system costs, we can see two interesting things. The costs increase, but the revenues decrease. If we look at the picture here, the colored stacked bar shows the total system costs. It's not very important to know the exact composition, but it's important to look at the black diamonds, which show the average generation cost, which goes up, and the gray triangles, which show the electricity price, so the price that the system receives, and this price goes down. We're talking here about a 20% increase in cost and an 80% reduction in electricity price. The increase in costs is caused by two reasons. First of all, the investment costs of intermittent renewables have decreased significantly by 2050, but they're still a bit higher than the investment cost of the other technologies. Secondly, there are integration costs to make intermittent renewables fit properly into the system. And these make the overall system cost more expensive. An important component of these integration costs are the so-called profile costs, which are caused by power plants operating fewer hours per year. And you can imagine that when you have a gas-fired power plant and when its capacity factor decreases, the investment costs of that power plant have to be borne by a smaller amount of running hours, so the overall generation costs of that power plant increase. This is the process that is happening. And overall, you can say that the integration costs and increased investment costs are both 50-50 responsible for this increase in capital cost. For this increase in total system costs. Secondly, we can see a reduction in electricity price, which is caused by the lower marginal costs of intermittent renewables. And the combination of this higher cost and the lower price is actually leading to a system which is not economically viable, because the costs are not covered by the revenues. And this might be a serious problem, because these systems are relatively cheap. At least they're partly optimized. These are, from a societal perspective, these are desirable systems. But from an economic perspective, they're not. So what you might see is that you get overall more expensive systems that are actually economically viable in the future, rather than these optimized least cost systems. But this is so that's looking at the least cost power generation. I'll just quickly touch upon options that can decrease the system costs by increasing the system efficiency as well. You can increase this system efficiency in two ways. By having flexibility options like the electricity storage, interconnection capacity, and demand response. You can use your power plants more efficiently. For example, you can increase the capacity factor of your baseload power plants. And you can reduce the curtailment that occurs in the system. So the switching off of wind and solar power when there's simply too much being generated. Looking at interconnection capacity and storage. In this picture, you can see the three scenarios, the 40, 60, and 80% rest scenarios. The different lines show the different capacities of electricity storage being added. And on the x-axis, you can see the interconnection capacity, which increases for different increases. On the y-axis, you can see the effect on the total system costs. Overall, you can see that when looking at interconnection capacity, that increasing interconnection capacity always increases system costs for the 40% rest scenario. For the 60 and 80% rest scenario, there is a sweet spot where the added costs of interconnection capacity are actually lower than the benefits which are caused by this extra capacity. So the total system costs decrease. When you further expand the interconnection capacity, this effect is cancelled out actually, because interconnection capacity is not cheap, is not free itself. Effect is relatively minor because we only use a crude 6-node system. In practice, it will probably be higher. Looking at electricity storage, we can see that in all scenarios, an increase in electricity storage capacity, in addition to the pumped hydro capacity, which is assumed to be at the current level, increases the total system costs. This is caused by the investment cost of electricity storage, which are still too high and in that way they outweigh the benefits, because there are definitely benefits of electricity storage, but the investment costs and the charging costs are too high. Lastly, I would quickly like to point out the effect of demand response on the power system. Again, we have the 40, 60, and 80% rest scenarios in this figure. And for every scenario, we have increasing amounts of demand response. What we can see is that both the generation costs and the fixed costs decrease when you have more demand response, because demand response can provide firm capacity, and it can act as short-time electricity storage by means of load shifting. Overall, demand response is a must-take option according to our results. So, to conclude, our study has shown that low carbon power systems can be realized with varying shares of IRS, so intermittent renewables, which are solar, PV, and wind power, in addition to other types of generators. We do see, however, that intermittent renewables increase the total system costs. An important complementary option to intermittent renewables is natural gas combined cycle power plants with carbon capture and storage, NGCC CCS power plants, because they are the least cost electricity generator. Especially the relatively low investment costs of this technology are interesting compared to other fossil fuel fired low carbon power plants. In addition, we see that gas turbines, demand response, and interconnection capacity can also reduce system costs, but electricity storage is too expensive. I'd like to thank you for your attention. If you have any questions, you can mail me or Machteld van der Broek. And again, you can also look at our paper, which is to be published in Applied Energy in the next 2 weeks, or mail us for a copy. Thank you very much, and I'd like to give controls back to Andy.
Thank you, Anne Sjoerd. And thank you to both of our presenters, to Machteld and Anne Sjoerd, for their excellent presentation. So I would like to start our panel discussion by certainly encouraging you to ask more questions, though we do have plenty here to get started with. So I will crack on. So the first question we've got, did you account for flexibility constraints within your study?
Yes, we did. This is actually an important component of these systems in which power system flexibility is becoming more and more important. We account for ramp rates of power plants, minimum load levels, park load efficiency levels, and startup costs.
Okay.
And then we use yeah, that's it.
It seemed that ocean power or wave power, tidal power didn't feature in the study as it was. Did you consider that as, or would you consider that as intermittent or more baseload?
Yeah, ocean power is an interesting one, just like concentrated solar power, for example, because in some ways it's very predictable. It depends on the way, on the type of ocean power that you're using. For example, tidal power is very predictable, so it's probably easier to integrate in your power system, whereas wave power can be more variable, as I've seen in studies. We did not include these options because if you look at projections, this type of generation is growing, but only very slowly, and by the year 2050, power is largely generated by other sources. But I think it's definitely an interesting option to further explore, especially when you're going towards the year 2100.
In terms of the cost assumptions that you made, did you assume learning in terms of, so it was really what degree of sensitivity were there to changes in assumptions around cost reduction of some of these technologies going forward?
Yeah, well, I think largely, roughly speaking, there are two types of costs or changes in costs which are important. First of all, there are change in fuel costs. If we also performed the sensitivity analysis, which I didn't touch upon today because of time constraints, which you will be able to find in the final paper. We see that if biomass becomes a lot cheaper, or when coal becomes relatively cheaper, that these types of power plants take over from the natural gas power plants, which can be expected. But you need pretty serious changes in fuel prices for this. In addition, we also varied the investment cost of intermittent renewables, but this does not affect the results much because because the intermittent renewables are put in exogenously, so we fix them beforehand. And we do see changes in the final cost, of course, but you do need out of the top of my head, I think a 30% reduction in all investment cost of all intermittent renewables if you want the 40 and the 80% rest scenarios to be equal in cost.
Okay. How does the electrification of heat and the transportation system potentially affect your results?
It can affect the results in two ways. First of all, it can affect the demand pattern. If you have more electricity demand from transportation and heat, patterns can change and they can be better aligned with the intermittent production or less optimally. Also, peak load could increase, which will make the total system more expensive. That's one thing, so the load patterns. Secondly, they also have the ability to provide more flexibility to the power system. For example, by power to heat and heat storage, or electric charging of your electric vehicles, which can perhaps lower overall system costs.
When you considered compressed air storage, did you focus on sort of costs associated with geological storage of compressed air or on surface tanks with pressurized gas or air? Is that a distinction that you made?
We did not go into such detail. We treat it more as a family of technologies. We are talking about geological storage here.
Okay.
And we also took data from geological storage.
Yeah, that's
we used also the previous study for these cost data, and we implemented those. Yes.
Thank you. Fixed operation and maintenance costs seem to increase with higher use of RES and RS. How can this be explained given that renewables, it's believed that renewables are expected to have lower operation and maintenance costs compared to conventional generation?
I think it's important to distinguish here between fixed and variable. When you have intermittent renewables, the variable operation costs are generally shown to be lower compared to thermal power plants. But you will have wear and tear, especially for wind turbines, for example, in offshore locations, which is pretty much constant whether they're running or not. So it's a fixed type of cost, an annual cost. So you basically see a shift from more variable cost to more fixed cost, and the fixed costs of intermittent renewables can be significant.
They also include, in this case, in the graphs, I believe, the investment cost. So that's maybe the confusing thing.
Let me just check. No, we grouped all the fixed O&M costs together, and we distinguish between the different investment costs. But yeah, the higher fixed O&M costs of the intermittent renewables make the total fixed O&M cost increase, whereas the operational costs decrease.
Okay. In terms of the options to adapt electricity market mechanisms that would realize these lower costs, is that something you consider in terms of what the options would be to deliver this?
I'm sorry, could you repeat that question, please?
What are the options to adapt electricity market mechanisms so that society can realize these lower costs?
I think broadly speaking, two options are being explored now in Europe and also in the US. You see that improved energy-only markets, in which governments say, okay, we will really let it function as a market now. We implement clear price signals, and we will not intervene. That's one path. Another path is to roll out capacity markets, in which you make payments to providers of firm capacity to make sure that you actually have this capacity in the system. Those are the two main options right now.
Okay.
And in the first system, you should then allow for really high peak prices, which is not currently happening. That's
Okay. Are the flexibility requirements as they are defined in the grid code now currently, or are they did you simulate for a different scenario?
What we did is we did not consider the grid codes. We looked just at the flexibility that will be required by the system in the future power system. So on the one hand, we looked at the flexibility that's required to adapt to the changing residual load, so the load minus generation by intermittent renewables. And secondly, we also considered two types of reserves, spinning reserves and standing reserves, which always had to be available in sufficient quantities. And these reserves, the size of them is based on the intermittent generation as well as the load. So from those two elements, so the variation in residual load and the requirement for reserves, we determined the flexibility that the system needs.
One of our questioners noted that it's an interesting observation that natural gas combined cycle with CCS has come out as lowest cost. Do you feel this would be different if you looked at other regions of the world, such as China or North America? Is this a specifically European result?
Well, it depends also on the resource prices, of course. I can imagine that currently in the States, natural gas prices are relatively low. So yeah, gas-fired generation will be more attractive than coal-fired generation, whereas in China, you can argue that the opposite is the case. That's one thing. Another thing is the climatological conditions. In Europe, we're relatively northwards compared to the US and China. And this especially affects the solar PV generation patterns. If you are close to the equator, solar PV will generate more stably, and the production by solar PV will also coincide better with peak hours of electricity demand. This could both affect the results.
One other thing is, I think, the CO2 storage capacity, which may differ around the world.
That's a good point too. Yeah.
Okay.
So those are some elements that could affect the results, and I would say that because it gets all really complicated, because you have all these elements which are interacting with each other, that you would have to look carefully before you can draw any conclusions about that.
Did you give any consideration to changes in, I guess, distributed generation, specifically home power generation and storage, which we could face? Specifically, there's a hypothesis that home power consumption could be almost levelized through the 24-hour cycle if these technologies become more widespread.
No, we did not do this. The perspective we took in this study is a very really centralized perspective, as you might have seen. If the whole power system goes in a more decentralized direction, you might see different developments. But I would be curious how you can generate electricity also in wintertime in Europe, because our results show that if you look, for example, at Germany, the Netherlands, and the UK, that about 80% of all power, solar PV power, is generated in one half of the year, and the remaining 20% only in the other half. So you would have to look closely at how you can provide power year-round, and whether that is actually cheaper than a centralized system. this is not something we investigated, and I think it's really interesting to look more closely to decentralized systems. But also for now, it's hard to envision how these decentralized systems might come about and how they will function, because they're not really widespread. And one other thing is that we currently have a very advanced centralized infrastructure. And I think this has certain advantages if you want to go for a future centralized system. If it would not have been in place, which is what you see in some regions of the world, decentralized might be more attractive than the situation that we have here in Europe right now.
We're coming to the end of our allocated time. I'm going to ask one final question to wrap things up. Overall, is CCS indispensable in low carbon power systems, or are there other sources that could potentially take its place?
If you're willing to pay enough, then other systems can also generate your required electricity. You can go really heavily on primarily nuclear power and biothermal power, and then you would not need the CCS. What our results show, however, is that these systems might be significantly more expensive than the systems that we have simulated in this study. And if you look, for example, at the IPCC, they predict that if you do not use CCS at all in the complete energy system, energy will be twice as expensive as in a situation in which you will use CCS. So it's not indispensable, but it will be a lot more expensive.
Actually, we are going to investigate now also a system with 100% renewables, electricity system, to really assess the costs and the cost differences with the systems we presented today. So hopefully we have an answer in the next half year on this.
That will be very interesting, Machteld. Thank you. That brings us to, I think, a neat conclusion to our webinar. I was able to pose most of the questions that we received, but not all of them, fortunately. There's a lot of interest in the subject, which I would take that as a positive. In closing, I would like to give, again, a big thank you to our panelists, Machteld and Anne Sjoerd from the University of Utrecht and the Copernicus Institute. Thanks you to both of you for taking the time to prepare and deliver your presentation, and for answering the questions that we got in so much depth. And thanks again to everybody who is on the call, who is participating, and for the quality of the questions that we were asked today. If you did miss part of the presentation, or you have a colleague who missed the presentation and could be interested, we will be making a full recording of the webinar with the panel discussion available on our website in the next few days. Also, we're always pleased to answer any further questions. We'll try and get those responses to those, so please send them in. We'll put them together and talk to our panelists to see if we can produce some answers. I'm sure you join me in thanking the presenters and the work that's gone on. Feedback is always welcome. This is one of a series of webinars on key topics that the Global CCS Institute brings to you. If you have any ideas for topics, please feed them back to us, and also feedback on the quality of today's presentation. In conclusion, I'd like to thank you again, and we look forward to bringing you our next webinar.